All right. Hi, folks. Thanks for sticking around for the last set of talks. Yeah, I'm Tobias, and I'm presenting joint work with Baldat and Cate, who's based at the University of Amsterdam. So let's get right into it. When people program, they have to concern themselves with flow control, right? So which things happen, and in what order, and under which conditions. And there are many ways to express this. For instance, you could draw a flowchart. But flowcharts can get very big and very complicated and hard to read. So what we really do is we tend to express these things using code. Now, this is all well and good, but sometimes this intuition that if I have a flowchart, then I can render it in code breaks down. As an example, let's consider this flowchart right here. And I think it helps to go over the details. So what you have here is, let me indicate it here. We have a program that starts, and it checks whether a condition A is true, right? And if it's not true, then the program stops. But if it is true, then we will execute some. And then we'll check again. And if it's still true, then we stop the program. But if it's not, then we run X again, and then we start over. And you can look at this for a while, and you can scratch your head. And eventually, you'll probably conclusion that this program can be informally described as follows. If A is true, then repeat X while A is changing, right? So if A has the same value after executing X as it had before, then we stop the program. And rendering this in code can be quite a puzzle. One way to go about it is, and this is actually corresponding to one of the automata that Chung showed you a moment ago, is you can use a loop with a break statement. And this kind of reveals why it's hard to render this in code, because here you have a loop that goes back and forth, but there's no clear exit condition on the loop, right? On the left, we exit if A is false, while on the right, we exit if A is true. But here we have a while loop, and we can end it prematurely in the middle by using a break statement. Another way of doing it is by introducing an extra variable to keep track of where we are in the flowchart. And you've also seen an example of this in the previous talk. And you can also just throw up your hands and say, I don't know, but I can use gotos. So this is also a valid implementation of this, this flowchart. And finally, and I did not put this on the slide, but of course you can also use like till recursion to implement this program. So these are all code renditions of this flowchart, but they all have, well, let's say, slightly objectionable features. On the one hand, the two programs that have break and return have non-local flow control, right, which makes them hard to validate and to analyze. And this program with the flag, well, it introduces something that was not part of the original flowchart. All of a sudden, there's this variable hanging around, and we're, yeah, not quite sure where that came from. And so you might ask yourself, do we need these things, right? Do we need these extra features to implement this seemingly simple flowchart? And the answer is yes. And examples of cases like this have been known since the 70s, of flowcharts that can be hard to implement using traditional code and where you need these non-local flow control features. So if having just if, then else, and while is not enough, what do we need to express everything? And there's a range of options that we can go with. So we just seen the break statement. And it turns out that having a single level break statement gives you more expressivity. For instance, you can express the flowchart that we saw before. But even then, there are things that you cannot express. If you have multi-level break statements, which some languages do have, then you can express everything. And having variables also always lets you like sort of simulate the flowchart, right? Like you keep a variable, where are we in the flowchart? So you basically implement that. we go. No worries. All right, check, check. Great. But as I said, these features in programming, I mean, they can be quite, well, they can make your program harder to analyze, right? Having break obscures your loop condition. It's no longer clear when your loop is terminating. Having multi-level break makes this problem even worse, and there are very few languages. Can I use this? All right. All right, so, and using variables to make your flow control explicit, or well, make it implicit by putting it in the data flow can make your code harder to read as well. And non-trivial till recursion is also not ideal always. And that's before we even start to think about giving a semantics to languages that have these features, right? If you try doing that, then, well, you might end up looking like that. So we asked, are there local control flow primitives that can express all deterministic control flow? So, for example, maybe there was something that we were missing, right, in our original tool set. Maybe if we just have if then else and while, but also the repeat while changes program that we saw before, maybe then we can express everything. Who knows? Unfortunately, as you might be able to tell from the title, the answer is no. And there's a little caveat, which is that if you allow yourself to have infinitely many primitives, then yes, you can express everything. But let's not go there. So, how do we prove this? How do we formalize this? We turn to Kleene Algebra with tests. And if you don't yet know what that is, don't panic. Basically, it's a way of expressing the kinds of behavior that your program can express using what are more or less regular expressions, right? Like you write a regular expression for the types of things, for the patterns of behavior that your program can do. And you can put little Boolean assertions inside to annotate under which conditions these things are executed. So as an example, I can have if then else, the traditional if then else like this. And I can write a Cate expression for it that looks like this, where there are two non-deterministic branches. In the left non-deterministic branch, I check whether B is true and then run E. Whereas in the right non-deterministic branch, I check whether B is false and then run F. Now this program has non-determinism, but it still is deterministic because only one of these two branches survives, right? B is either false or true. And here, we can simulate a while loop using Cate by writing this Cate expression, which says, run the body of the loop some number of times, and each time the condition is true, and finally, when you're done, the condition is false. So this also describes the pattern of behavior that you would see using a while loop. Now, Cate comes equipped with a relational semantics, and the way this works is you take a predicate for every test letter, and you take a relation on your state space for every action, and that'll give you a way of moving from Cate expressions to relations on your state space. And because this is POPL, I think I can get away with writing this as a dependent type. Now, because, as I said, Cate expressions are basically glorified regular expressions, that means you can model them using finite automata, and you've seen these also in the previous talk. And there's so the way you read these automata is you have transitions that have two things on them. This says you can take this transition if T1 is true, and this says when you take this transition, execute the action P1. And here we have these double arrows that say when a state can accept. So this state can accept if both T1 and T2 are false. And again, because we're doing this in a regular setting, these automata have a close one-to-one correspondence with expressions. So everything you can write using a Cate expression, you can also do using an automaton, and vice versa. It's basically a version of Kleine's theorem. But remember, we were interested in deterministic control flow, right? So, and I said that Cate expressions can have non-determinism because of the plus inside. So how do we select the expressions that are deterministic? It turns out there are two ways of doing that, and they are equivalent, fortunately. So one way is to say, okay, take the semantics of your expression. You can supply it with an interpretation of your primitive letters. And if you give it an interpretation that assigns a partial function to every letter, not just a relation, but a partial function, and you get out a partial function always, then we call that expression deterministic. But equivalently, you can say your expression is deterministic if its automaton is. And these are the same thing. So this is a robust notion within the theory that we're working in. So we've already seen some deterministic expressions, right? I already explained that this one is deterministic because only one branch survives. And by similar arguments, you can show that there's no non-determinism here either, because either you continue with your loop or you halt. So let's put this theory to work. Here's an automaton for the expression or the idea that we saw before, which is that we need to repeat some program P while some test T is changing. You can think of this as a flowchart, but as an automaton it looks like this. And because of the correspondence between automata and expressions, you can also render this as an expression, and then you get this little monster right here. And this is also a deterministic expression because it comes from a deterministic automaton. So now we have a new primitive for flow control, in addition to the if, then, else, and while that we saw before. So we can just write this as a, well, direly needed shorthand for this right here. And now we can formally state the thing that we observed before, which is that if you build expressions using if, then, else, while, and sequential composition, then you cannot build any expression E, right, that is equivalent to this repeat while changes program. And again, referring to old work from the 70s of people that were already aware of this, but they weren't using Cate. So, all right, so these are known results, but where are we? Basically what we did is we developed this hierarchy of different kinds of expressivity. At the very top, we have Cate, and we feel like this is a reasonable ceiling because here you can write everything that you can write using an automaton, or equivalently anything you can write using a flowchart. So basically anything you can dream of. And within this, we have the deterministic Cate expressions. And inside that, there are the expressions that you can build using sequential composition, if, then, else, and while. All right. And I just argued that if you add the repeat while changes thing as a primitive, then you get a slightly larger set of behaviors that you can express. And on top of that, so what we actually showed is that even outside this blue zone, right, there's another fragment where there's some other spooky operator that you can add that is more expressive than the blue circle, but less expressive than the stuff in the green circle. And this goes on infinitely. So even beyond this, there's another fragment of deterministic Cate that cannot express everything, but is more expressive than this. And you can just keep doing this. So this implies a hierarchy in terms of what can be expressed. So formally, what we showed is that for every deterministic fragment of Cate generated by finitely many operators, there exists an additional Cate expression that cannot be expressed using those operators. In what little time I have left, I can try and give you an idea of the proof. If you want the full gory details, then I'm going to refer you to the paper. So here's the idea. If you have an expression, for instance, the one for sequential composition, you can turn that into an automaton. And in case of sequential composition, the automaton looks like this, right? You first unconditionally run P1, then you unconditionally run P2, and then you unconditionally accept. Fine. You can also have if, then, else, and the automaton looks like this. So here, if T is true, then you run P1, you go to Q1. If T is false, you run P2, you go to Q2. In both cases, you're done. And you can also have an automaton for while. And the automaton looks like this. You have one state, you loop while T is true, and you run P, and otherwise If t is false, then you accept, then you're done. Now, if you look at this automaton, it has a sort of behavior that, wait, let me take a step back. Composing these expressions, right, means that you're also kind of composing these automata. So we have a way of making that clearer formally. And it turns out that if you compose automata like this, you will never be able to build an automaton like this, where there's two states jumping back and forth, but they have possibly contradictory ending conditions. But now if you add this automaton, which corresponds, well, it's not quite, but it's very close to the repeat while changes program, right? If you add that to your set of expressions that you can use to build more flow control, then there's another automaton, which is kind of a generalization of this two-state automaton that you cannot express. And this goes on, right? There's even a four-state version of this one, so there's an infinite family of things that you're going to need to add to express everything. So that concludes the technical part. So these automata satisfy a property that we call them all one-dense. And this automaton right here we call two-dense, and this is three-dense. And what exactly that means is, well, I'm not going to tell you, but it comes down to how connected the automaton is, how clique-like it can be. And so all of the automata that you built using the traditional flow control operators are one-dense. And our question is, does this characterize all of the automata that you can build using GCAT? We don't know. And we don't have a very good handle on it right now. Also, we wonder if this result is still true for extensions of Cat. So there's some buzz around Kleene Algebra with tests in domain lately. You can also look at Kleene Algebra with tests in intersection. And I mentioned a result, well, I obliquely mentioned a result by Kosoraju earlier, which implies a sort of hierarchy in terms of what you can express if you have multi-level breaks, right? If you have single-level break, you can express more than not having it. If you have two-level break, you can express more, etc. So how does our hierarchy compare to Kosoraju's? And finally, we wonder if there's a different kind of composition that can incorporate maybe n-level breaks, so perhaps algebraic effects. That's all I have for you today. Happy to answer your questions.
Okay, so let's thank for a great talk. We can take one or two questions.
Question. Could you give some intuition of what kind of control flows are non-local? Like there are some examples, but is there some general criteria to determine which is non-local?
Yeah. So I don't have a very crisp definition for you, I'm sorry. It's just anything that uses break or goto, I'm calling non-local.
Okay, sounds good.
Yes. In contrast, so I guess non-local is the bad thing. The good thing is something algebraic, right? Where you can have where you can compute the semantics of it by computing the semantics of its operands and then putting those together. So if then else, or you can compute the semantics of the if, so the if branch and the else branch, and then compose those. And that's what we want.
While it's also local for that reason.
Yes, yeah.
Okay, so thank you for the question. Yeah.
Thank you for the talk. I have a slightly high-level kind of question. What do you think about adding parameterized operator that can cover any n-dense thing? Yeah.
So in our paper, we eventually have, like, towards the end, we have a positive result, which does something like you're proposing. So basically, we introduce a kind of parameterized or an infinite family of operators that kind of corresponds, it's kind of a template for like n-wise tail calls that you can use. So I think that sort of covers where you were going, right? Yeah.
Okay, so any more questions? Okay, let's thank Tobias again for his great talks.